All right, guys, we're day 2 on parametrics. The idea of a parametric equation, remember, was it had 3 variables, but we only graphed 2 of them. So we're finding x and y in terms of t. Does that sound familiar now?
Yeah.
Okay. So how are we going if we're doing this one by hand, how are we going to decide what values of t to plug in? Yes. They have to give us restricted values if we're going to do one by hand, okay? We're going to do some on the calculator where they don't give us restricted values and we just have to kind of play around with it. But for this one, they give us -3 to 1. So we're going to go -3, -2, -1, 0, and 1. The other thing is if they don't give us restricted values, there's no way for there to be endpoints. Okay, the endpoints are going to occur at -3 and at 1. How do we find the x values for this particular graph? Okay, we use this little rule up here. It said t squared minus 1. So this squared is 9, minus 1 is 8. Squared is 4, minus 1 is 3. Squared is 1, minus 1 is 0. -1, 0. Okay, how do we find the y values? It says this rule. Remember, we're not using x. We're using t. Sometimes I get messed up and start plugging x's in here. But it's supposed to be 2 times the t plus 5. So 2 times this would be -6 plus 5 is -1. Am I doing okay? -4 plus 5 is 1. 3, 5, and 7. That seems okay. So we can do 2 things. We can graph it and we can tell the endpoints now. When we go to graph it or write the endpoints, which of those numbers do we write down? The x and y. So the endpoints occurred at 8, -1, and 0, 7. The other thing we need to be careful of is as we graph, we need to keep track of kind of the order the points are going in so that we can graph arrows for the orientation. So if we go 8, -1, 3, +1, 0, 3, where am I at? -1, 5, and 0, 7. It kind of went like a candy cane that's fallen over or something here, right? It's going in this direction. It's a piece of a parabola. Everybody okay? Any questions or comments about the graph? Yeah, it's not weird graph paper, but it's kind of tiny graph paper. Still painful, yeah. I agree. All right, when we go to graph this, if you weren't here the other day, the T is going to have its own category in the window. And our T window is going to be defined by this up here. So it's going to be -3 to +1. The T step we use, we want to make it small. So there's a lot of increments between here and here. We usually just use 0.1. If you make it incredibly small or incredibly big, you either won't get a graph at all or it'll take it forever to graph. That being said, we're going to do one in a minute that we're going to want to use something different than 0.1. Okay. That's called T-step when we get in the graph. What kind of a window do we want for X and Y before we try to plug this in? Okay, we could do -2 to 9 or even like -3 to 10 and -3 to 10. You could do -10 to 10 and it would look just like that one right there, right? Okay, so again, if you missed the first half of the lesson, you go to mode, you make sure you're in parametrics. Can I ask you all to make sure you're in degrees today, guys? As well? We're going to do something that we could do in radians, but we're just going to stay with degrees because we need those for the application problems later today. All right, and I use this feature today. I'm going to show you something cool later. I'm going to put mine in simultaneous. So anything I put in X1 or Y1 and Y2, it's going to graph them at the same time. You can turn that on if you want to try this later, but it's something I'm really just going to demonstrate. All right, so we did -1, nope, -3, just kidding. My window is -3 to 1 by 0.1. And we did something, -4 to 10 and -4 to 10 seems like it would be okay, since it's already in there. And I'm gonna do some crazy stuff later, but for right now, we were supposed to just put in t squared. This is in the y equals window. Okay, x rule was t squared minus 1, and the y rule was 2t plus 5. How did we get a t again? This key right here that had x, t, theta, and n, that key works depending what mode you're in. In function mode, it gives you an x. In parametric mode, it gives you a t. So that's the key we're using. All right, graph. Does that look like ours? Okay. If we had wanted to go to the table, we could have also found ordered pairs there. We had a defined window of -3 to 1, so we would have just used those ordered pairs from the table. Any question? Yours is flipped? Ah, did you put your x and y in backwards? The t squared minus 1 has to be in the x, and the 2t plus 5 has to be in the y. That's a brilliant observation, because we're going to talk. You didn't do that? Can you bring it here? Yeah, we're going to talk about this in a minute. Have a -1 instead of a -1, I think. You had it in as a -1 instead of a -1.
Where?
In the y equals, it was a negative sign instead of a minus. All right. So whatever you had here for a window, I really didn't care. All right. Then we did this whole eliminate the variable thing. And what we did last time was we solved this x for t. So we made x plus 1 equals t squared. I'm not writing this in the blank for a reason here. And then if we square rooted, what would we have to remember to do? Yeah, it would need plus or minus x plus 1 equals t. And then it said y was 2t plus 5. So we would have put this mess in here and gotten y equals, and the 2 is multiplied by the t's, so it would have been plus or minus 2 times the square root of x plus 1 plus 5. And that would be a fine answer. But I'm thinking most of us would have forgot the plus or minus. And if we forget the plus or minus, we only get half of this. Okay, it's like a parabola, and we'd get the top half and not the bottom half, or whichever, if we didn't put in the plus or minus. What I might have done for this question is, because this was the linear piece, the y, can you solve, whoops, that's supposed to be an equal, sorry. Can you solve that for t, guys? What would that say? Y minus 5 divided by 2 equals t. And then we could put that into the other one, so it would say x equals t squared minus 1, only in here we're going to put y minus 5 over 2. Was that a little bit easier? And I don't really care. As long as you get rid of the t, I'm fine. If x's and y's, that's all it means, is x's and y's, no t. Eliminate t, okay? With this form, guys, if we had added the 1 over to the other side, squared the 2 down here, and multiplied it over to the other side, it would have looked like this. If we had more time and hadn't had technical difficulties at the beginning, I might have even spent some time talking about this parabola. There was a squared there, sorry. Because some of you really messed up this parabola business on the quiz yesterday. This number right here is for p. So p is 1, okay? Some of you thought like the 4 was magical and somehow. The 4 goes with the P. It's 4P equals 4 on this one, so P would be 1, which is the distance to the focus. All right, moving on. I have a really cool thing to show you. If you will take your calculator and go to y equals and type these two in for me. Okay, drag this out of the way. Come on. There we go. In x, put 2 cosine. Okay, now I dragged it too far. Notice over here it says when graphing parametric equations, theta and t are interchangeable. So instead of theta, we're going to put a t. So I want you to go to your y equals screen and write 2 cosine t. And in the x in terms of t, write 4 sine t. Now, if we're doing sine and cosine, normally we're graphing, we're in radians, yes? So what would an appropriate window be in radians, maybe? Zoom trig, but if we're putting in t steps, what numbers might we put in for t? 0 to 2 pi? Does that make sense a little bit? If it was in radians, if it's in degrees and we want to do 1 rotation, we might go what? 0 to 360. And we left our calculator in degrees, right? So for my t window, I'm going to put 0 to 360. So it's going to try 1 complete revolution, okay? Now, this is where my t step is a problem. If I put in 0.1, it's going to calculate 10 for every 1, so it's going to do 3,600 calculations. It goes kind of slow. What could we count by instead? 1s or 10s or something? Either one is fine. Okay, I'm just going to put 10 so it doesn't take too long to graph it. Now, I'm going to go down to this and put -5 to 5 maybe for both x and y, and that's just because I know ahead of time that those aren't too bad of numbers. All right, now hit graph and see what fun happens. Interesting. It looks like a circle on my screen. It's actually an ellipse, just like Basma said. Can you tell why it's an ellipse? Yes, see how it goes 2 this way and 4 this way? So what we can do is what's called a zoom square, because right now our screen is stretched funny one way or the other. So do a zoom square or zoom 5, and that stretches it out equally so that it's square instead of rectangular. It still looks like a rectangle, but the units are the same length going across as they are up and down. That's what that feature does. Now, it is pretty smooth. If I changed my t-step to like 1 instead of 10, it would just be a little bit smoother curve. Notice when it was a circle, it was kind of jagged because we had counted by 10s, but it does take a lot longer to graph this. All right, so I want you to throw this picture onto your paper. Oh, you don't even have this question, do you? Do you have it? Okay. Oh my goodness. Yeah, draw a nice ellipse. 4, 2, 4, 2. That is the worst graph ever. Usually I can at least. Yes, you do. That's a little bit better. Okay. Now, I want to talk through this because this is a revelation for a lot of students. Do you remember when you did things like x minus y equals 7 and 3x plus y equals 9, and you said, oh, I want to get rid of the y, so I'm going to add these magically together so the y drops out. Remember that? That's kind of how I think about this process. You cannot take x equals 2 cosine of theta and y equals 4 sine of theta and get the theta by itself and substitute in. You will have a hot mess. Okay? You would like x over 2 inverse cosine, but that doesn't really get rid of, and then you'd have the inverse cosine of the sine of, it's just a mess. So you need to be paying attention and think about memorizing this idea because it's not hard, but you got to think about it when you see sine and cosine. Here's what we're going to do. We're going to divide by the 2, so we're going to have x over 2 equals cosine of theta. divide by the 4, so we have y over 4 equals sine of theta. Okay? Now, if I added those together, it wouldn't help much, but we are allowed to square both sides of an equation. Okay? That's kosher. You can square both sides of an equation. Now, if I add this to this, I get x squared over 4, because I squared those, plus, down here I get y squared over 16. Everybody okay where I got the 4 and 16? I just squared them. Equals cosine squared plus sine squared, which is 1, which eliminates all this. Now, does that equation look very much like something you had a quiz yesterday for an ellipse? Okay, so we're used to that equation of that ellipse, yes? That makes sense. All right, so can you quickly do these two? It's the exact same concept. I just want you to practice it so that you get it drilled in your head, okay? One of the questions asked by earlier classes today was, are we going to have to know other identities? Like, is it no? The answer is no. Basically, we're only one we're going to worry about is this sine squared cosine squared equals plus cosine squared equals 1, okay? It's not like you're going to have to do something and trade it for tangent or... And I'm not going to give you any crazy ones. There's just going to be one problem that looks like this. So over here we get a sine squared plus a cosine squared, which we're just going to say is 1. Okay, so if I skip all those steps, anybody have this one done? Yeah, I was just doing it. Anybody confused? I can go back over it. I can go slower. We're good? And you could write this in the other order, right? Like Basma read it. It's all good. Okay. Now, do you remember inverses? How would I find the inverse of, say, that? Switch it to x and y, and then what? Yeah, and then to get rid of the 1/2, you'd multiply a 2 over here. Remember all that fun? Inverses. Well, the inverse idea was switch x and y. If this is the rule that generates x, and this is the rule that generates y, how do you think we could do an inverse? The x rule is now going to be, and the y rule is going to be 3t minus 1. Now, I guarantee that on the quiz, if I ask a question like that, somebody's going to start like adding 1, dividing by 3, and then putting that over here and do. All you have to do is switch the rules. Does that make sense? That all we're doing is switching the x and the y, how we get the x and y numbers. All right, we're going to graph this. It does say to use -10 to 10 for t. I just want you to see that they are inverses because do you remember what an inverse does to the graph? It flips it across a particular line. Do you remember the line? Y equals x. Yep, because remember that's what we're doing is we're flip-flopping the x's and the y's. All right, so put the original one in y1, x1 in y1, and then flip-flop them. I am going to over here and okay, it said for the window to use -10 to 10. T-step of 0.1 or 1, either one is not bad. I think I have a square window already, so I might leave it. Otherwise, you can try a zoom square, which is 5. If it's not big enough, ooh, So one is a parabola whose vertex is over here somewhere, and the other is a parabola whose vertex is the same spot but down on the y-axis instead of the x-axis. Okay, so it says to sketch. Really, again, with the no working. Oh, there it is. Why am I writing over there? Everything is a mystery. How all of this works or doesn't work. Okay, so we got a parabola that was over here and had a vertex around there, and the same parabola was going this way, and yikes, that's horrible. And they're supposed to be reflected across the line y equals x. Yeah, that's a line. Okay, that was the worst picture ever. You're right. I'm having a bad picture day, period. Okay, can you do this one real fast? Yeah, the color makes this one way more fun, but I don't have... I can show you a little bit of how to do that. When you go down to y2 or to the second equation, arrow to the left a couple times. Yes, you can, if you hit once, you'll get a bold for x2 and y2. And then just remember to switch them around. And I don't think we need to change our window. Maybe we do. It's not great. It is not actually two lines. Can you tell from the equations what it's supposed to be? Yeah, it's a square root graph. I'm going to try -10 to 10 for my x. And then try a zoom square, see if it fits a little better. I really not picky about this question, but okay, so this is what I'm getting. It's still cut off at the bottom, but okay, I have a skinny little square root graph going this way, and whatever value that is, it's the same value down here going this way. Yeah, okay. Those are obviously perfectly the same size. Sorry. Any questions? Get the basic idea of graphing inverses. Okay, now this is more of a demonstration. If I take time to make sure you all get this graph going, it's going to be kind of miserable. But do you remember earlier this year when we did problems where you threw things up in the air, the equation looked like this with x's instead of t's, yes? This would have been initial velocity of 90 from a height of 5. We threw something straight up, right? There's no sine and cosine like we did the other day, indicating we've thrown it at an angle. It's going straight up. All right, it's kind of interesting, and I just wanted to show you this, that you can actually do this on here, and it's fascinating to me because the t-step calculation allows you to see the acceleration. Now, I will tell you that this number 8 is just a random choice that I made because I wanted it to be over on the right side of my screen. So this is what happens. What does it say to put the window to, guys? Okay, I'm actually going to go -50 to 200 so I can see this. Okay. Wasn't that fascinating? Did you see it? All it did was draw a vertical line. Okay. Let me show you, if I arrow to the left and I turn on this little thing that's called a tracer, but it looks like a little bouncy ball. I want you to watch really closely. Is everybody watching up here? Because it's not going to take long. Okay. First of all, it's modeling the actual path this time of a ball thrown straight up and back down because it didn't make a parabola, right? It just went up and down. But because it's doing all those calculations, do you see what happens with the pace at which the ball moved? It went, what happens as it reached the top and what happens as it came back down? Okay, watch one more time. I turned the tracer off this time. Slower, slower, slower. Actually, and then as it comes down, it does what? Accelerates. Is that not physics that you learned in physics? That, okay. As it, eventually at the top, the ball has an instantaneous velocity of 0, right? It doesn't, it's not like we can look at it, but if we did a slow-mo picture, it would freeze there and start to come back down. And it accelerates due to gravity as it approaches the ground, yes? Okay, I want to show you one more thing. We can actually do this on the screen. We can show both of those views. The views we learned the beginning of the year. All right. Come on. I think I hit it too many times. I want it to trace it. Okay, everybody watching? Here we go. So it's going to show both views. There's, yes, at the same time. Here's the height of the parabola, or height of the ball, as a function of time. One shows what we traditionally did. On the left, we drew a parabola because we thought of the x-axis as time and the y-axis as height. The one on the right is the little straight up and down guy is actually in terms of time, it's virtual, it's height because it's going up and coming back down. But you see them on the same screen, it's kind of cool to think about, yes? Did you want to say one more time or you got it? Okay, we'll do no tracer this time. How's that? Just watch the ball, okay. So it slows as it reaches the top, which the top is the vertex of the parabola, yes? And then as it comes back down, it accelerates. Okay. Why does our ball go underground? Because, well, I could change the time. I could try to stop it when it hit the ground, but I'd have to set my T to be like, 5.3 or wherever it stopped. Okay. You get the idea. There is another fun activity if you want to try later to do this one. It's really fun. It shows a ladybug flying across the screen and she like turns around and accelerates off one way. But I'm going to skip that one. I want to get to the actual applications that you have to do for homework. Do you remember we talked about this the other day and I told you something wrong? So I need you to be paying close attention. Did we change something on the back of the pink sheet? We changed it to 16, right? Because on the back of the pink sheet, it says, when you're finding the path of an object launched at an angle from an initial velocity, it was t initial velocity cosine of theta, and y equals t initial velocity sine of theta minus, it says 1/2 t, remember? Yeah, 1/2 gt right here. If it's, right here it says, if it's feet per second, you use 32. Well, half of 32 is 16, okay? And then it was plus initial height. But I told you otherwise we use 9.8, but it's half of 9.8, okay? So if it is in meters, you're going to use negative 4.9 t squared. You don't have to write that on the pink sheet because when we do it on a test or quiz, I'm just going to use feet. But there is a question on here and one on the homework where you have to use the 4.9. Okay, I just wanted to clarify that. So what are we doing here? Can anybody give me those equations? Oh, let's change this question. Because it's 80 feet per second and 80 degrees, which when you're doing notes, that doesn't really help you know where those numbers came from. So let's make it What do you want to make it? A little faster, a little slower? I'm going to go with 70 feet per second. If we make it really fast, we did 100 and that was fine, but the faster, then you have to get a bigger window going and it's kind of a pain. All right. So what would the x equation be? Do you remember it says you put in t times v sub 0, which we just changed to what? 70. Please make sure you changed it on your paper. You're going to look back and go, where did I get that number? Times the cosine of the angle, which is 80 degrees. I just think using 80 and 80 doesn't help you when you go to look at your notes to know which number went where. And this one is t v sub 0 sine of the angle, and then what? This is feet per second, so we're going to use 16t squared plus initial height, but what's the initial height here? Ground level, so 0, so you could leave that off when you put it in your calculator. All right, before we start, this is a toy rocket. It's being launched straight up into the earth. Oh, no, it's at an angle. It's at an 80-degree angle, though. So here's 90-degree angle, here's 80-degree angle. I don't think it's going to go super far away from us because it's a pretty straight up angle, right? But it's going pretty fast, so we got to think about this. What do you want to try for time? There's nothing wrong with trying because you just find out you need to make it bigger or smaller. If it stops in midair, you know you didn't put enough time in. What do you want to try for time? 10 seconds, and we'll try 0.1, okay? What do you want to try for distance away from us, which would be x? Just, what do you want to do? I think we're going to regret that one. Height. Okay, let's try it and see what happens. I think the 500 is going to be too big either way, but I just have done this question 3 times today, so. All right, so it was, I already forgot, 70, is that what we changed it to? Oh, I got a t first. T times 70 cosine of 80. Do I have it right, guys? And then t 70 sine of 80 minus 16t squared. Okay. I'm not sure we needed 10 seconds either, but that doesn't really hurt anything. I don't think it's going 500 feet away, but I'm going with you. Okay. Woo! Okay. So the height was pretty good. The 100 height was pretty good. But I'm thinking I'll change this x to 100. Okay. 70 is good. I will tell you that it's tracing along by 0.1s, remember, because I made my t-step 0.1. Did you make your t-step 0.1? So the better your window is, the little bit better you can calculate things. But let's just go with this. When it says, do you remember from yesterday, you can only change t, yes? If we go to calculate, we can't find an x-intercept, we can't find a y-intercept, we can't do anything. So this is all kind of a guessing game where we just have to look at values of t. How long will it take the rocket to travel 10 feet horizontally? What am I trying to get? Horizontally would be x, right? So I want to get as close to x equals 10 as I can, and I can't control that, so I have to just trace. What's happening? Trace. Oh, I got to trace to the right. I'm just hitting trace. Duh. Okay. Yeah, it's somewhere between 0.8 and 0.9. If you wanted to fiddle around, you could try things in between there, like 0.84, 0.83. But remember, I'm going to be okay with any of those. How long did it take is roughly between 0.8 and 0.9, yes? Is that what we said? 0.8 was the closer one? Because it said how long, okay? What will its vertical distance be at that point? What is that asking? The y value, right? How high is it? So when we got it close to 10, okay, I have 46. If we just use plain old 0.8, it's 45, right? Rounds to 45-ish. So somewhere between 45 and 46 feet away from us. High, feet high, kidding. Vertically. Okay, what is the maximum height that it ever reaches? Again, we can't control anything. We can just trace around. What are we trying to maximize? Yes, we want the y to get as big as possible. Okay, somewhere in here, but it doesn't, oh, what is the maximum height reached? Yep, okay. 74.2, it did ask that. And then how far away does it land? Okay, now what? Yeah, we want to find what to be 0. Its height, which would be y. We want y to be 0, not negative 0. Somewhere around there? 52.3-ish. Okay, we got 3 minutes. I want to do the golfing question because it has the different... Oh my gosh, I have something in my eye. Okay, this is a golfing question, but it's in meters per second. Do you see this? So what are we going to put in for x? T times... No, that goes in the y. This is still initial velocity. What is the initial velocity? 56 cosine of 12 and 56 sine of 12 minus 4.9 t squared, okay? And that's the goofiness because it's in meters. Now, window. How long does it take a golf ball to come down? I think 6 or 10 is okay. That would be really long. Can you hit one that stays in the air 60 seconds at the bat? All right, guys. How far away? Meters are like yards. You can hit a golf ball pretty far, right? Austin said 300, but it is less than 200 for this question. Height, it doesn't go as high as I would have thought. You could do 0 to 50. It's not even close to that high. All right, type it in, see what you get before I run out of time. What was it? 50? 56 and 12? Oh, I didn't change my window. 150 is really good. I'm going to leave 150, and I don't think I need 50. Yeah, it's the height, it doesn't go up that high. The question, though, is how far away does it land? That's really a weird shape. Did I do something wrong? It doesn't look like a parabola. What is that parenthesis doing there? I have a squared squared. I'm like, it should be a parabola. What is that weird shape? Now what do I have wrong? Oy. $130 is what I remember. What do I have now? Well, that shouldn't matter. Okay. Oh my goodness. I'm gonna cry. Okay, so what we wanted to really trace was the distance away from us when it hits the ground, right? So when y gets close to 0, it's about 131 feet away is the x value. It was meters, I lied, not feet. All right. So this is what you need to be working on, and there's some really fun matching at the end of this lesson, and no one's listening to me anymore because. Okay, get some really cool graphs. We'll mess with them tomorrow. Have a good night.